Okay, so it's my pleasure to announce that tonight's talk, which is entitled The Technical Aspects of Meeting Ofcom Requirements for Field Strength, which is by Mike G4CDF, but very kindly assisted by Dr. John Rogers M0JAV, who is on the RSGB EMC committee. So a warm welcome to you, John, as well, and thank you very much for joining us and taking part in our meeting. So with that, I will hand over with many thanks to Mike G4CDF. Over to you, Mike, and thank you very much.
Yes, thanks, Simon. Good evening, everyone. Well, I had planned to do this talk on my own, but rapidly realised that I didn't know enough about the Ofcom RSGB situation, so I put out a cry, and John answered it. And thanks very much, John. You're going to be on first, but I'll just put up my presentation if I can, and see if I can get that going. Where are we? Share, and then we go to.
Yep, we can see your screen, Mike.
Sorry?
Yep, we can see your screen, Mike.
Oh, that's good, but I wanted to try and
press F5.
F5, thank you. F5's not working. Anyway, I'll just use this for the moment and sort it out next time. I'm going to talk about measurement of electromagnetic fields, and well, this is the contents. So first of all, we'll get John to tell us all about the RSGB Ofcom calculator and with the work that's been going on between RSGB and Ofcom, and then I'll go into talking about other methods than that could be used to at least help to determine compliance with the EMF requirements by the other means, as well as the Ofcom calculator. So over to you, John, for your presentation. Thank you.
I think you'll have to, oh, you have stopped sharing. Good. Thanks very much, Michael. Hopefully you can see the screen. You got it all right?
Yep.
Goody, goody.
Yep.
What's that doing over there? Get out of the way. I was trying to open up the other half of the PowerPoint presenter, but it decided to put it on the wrong screen. So that's the official title of the Ofcom license change, which is expected to come into force towards the end of this year.
John, if you're speaking, we can't hear you. I think somebody may have muted.
John, can you unmute?
Yeah, I've done it now. Yes, it said the host muted everybody, including me. Can you hear me now?
We can.
Sorry. Okay, so what the license conditions is basically going to say is that only if you've set up, you should only use your radio if it meets ICNIRP guidelines for exposure to members of the general public. And that's how Ofcom say that in, as usual, a few too many words. So what we have got, because we are in probably twice weekly discussion with them about the implementation of this, is an assurance that they want to foster a climate of compliance, and that's why we're talking to them, to try and help them ask us to do things in ways that we can do them. And they don't want to have a high-handed enforcement approach. One reason for that is probably that they don't have enough people to do the enforcement if they did try to have a high-handed enforcement approach. But they will act against anybody who is reckless. So that's the situation as opposed to the proposed changes. What are we going to have to do? We're going to have to perform an assessment that shows what level of electromagnetic field and how that corresponds with the ICNIRP regulations, and you can do that in one of 5 ways. You can follow the manufacturer's instructions. That may not sound very useful at the moment, but we're expecting that manufacturers will start to say, if you operate your handheld in this way, you will be compliant with ICNIRP. So if that is the case, in the future, that's a useful thing to have in there. The way we hope most people will be able to do it will be like, if you want to bake a cake, you follow a recipe. So we're hoping to put out a recipe book with pre-assessed compliant configurations that says, if you only use 10 watts, your mast is 10 foot high, and your antenna is whatever it is, then you will be compliant. So this will help people coming into the hobby who just want to get on the air and not worry about detailed calculations. The next way is to actually do some desktop calculations, and we have a calculator that we're working on which is based around the Ofcom engine. Ofcom are probably going to update that calculator in about 2 weeks' time, and we'll update ours at the same time. I don't think they're going to change the basic formulae that are used in the calculator, but they're going to change where it's applicable, and I'll come on to that a bit later. The other thing you can do, and this is perhaps the most useful one, is if you do have an area where the field from your system is above the ICNIRP reference levels, if there's nobody there, there's nobody getting exposed. And the regulations are not to expose people to field strengths. So if there's some way that you can prevent people, or keep a check on them and don't transmit if there's somebody there, a camera in the garden or something, then if you're not there, if somebody's not there, they can't be being radiated. The last way, which I know Michael's going to talk about, is taking measurements. It's a very valid way of doing it, but one, don't buy cheap field strength meters. There's a whole load of them appearing at the moment for a few quid. They measure the 50 hertz field strength. Ofcom won't accept that, surprisingly enough. Also, if you are going to do it properly, then you need some quite expensive kit. You will need to follow a procedure and a process, and you'll find that it's very difficult to take the measurements. But what we're hoping to do, and maybe get Michael involved as well, is to actually use some measurements ourselves in order to just validate the models that we've got going. Whichever way you choose of the 5 types, if you actually keep the records, then you can prove you're compliant. And the best way would be to choose your configuration that is known to be compliant. So what's it all about? Electromagnetic energy, basically, our bodies are effective at absorbing it. That will cause a heat rise, and normally by changing our blood flow, by sweating, faster panting, breathing sort of stuff, we can reduce the body's temperature. But strangely enough, if you raise the core body temperature by more than a degree, then it starts to take evasive action, which is potentially a health change. So it could lead to harmful effects, and that's why the ICNIRP has said these levels won't cause a problem, so stay below them. The problems are either heat or tingling nerves, electro sensitivity. So ICNIRP gives guidelines for limiting exposure. There are basic restrictions and there are reference levels. The basic restrictions are about how much energy you can absorb in watts per kilogram. That's impossible to measure. So they've done a lot of theory and said that if you keep your field strength below the reference levels, then you will meet the basic restrictions. There are two problems. One particular problem is VHF, where the human head is resonant, so the limits have to change. There are also two levels. There's what's called the occupational level, which is somebody who's employed and presumably understands it, and then there's the general public. Your exposure can either be local, like your head, or the whole body, and the limits are different for both the local and the whole body. There's also a peak limit for frequencies below 10 megahertz, and these have to be averaged either for 6 minutes for local exposure or 30 minutes. So it's sounds a bit difficult, doesn't it? What it comes down to really is that there's an area around your antenna where you might exceed the occupational limit. Then there's an occupational zone where you as an amateur could be present, but a member of the general public couldn't. And then outside of that, there's a compliance zone where you, if you are below, where you will be below the general public reference levels. And obviously, depending on the antenna, the zone shape will change. So, how do you calculate them? Well, ICNIRP have a really good 41-page document. They have some wonderful formulae. All this, it's a lot more complicated than it says. It says whichever is the bigger of the E field above its limit or the H field above its limit squared, that's the level that you have to calculate. It's again a bit different for the less than 6 minutes, but don't worry, you don't actually need to do that. It's all done for you in ICNIRP, and they come up with a way of comparing the electric field, the magnetic field, and the power density with these exposure limits. But don't worry about that, because that's quite easy. There's some graphs. These graphs are built into the calculator. There's one thing I just wanted to, let's just explain them. The dotted red line is the electric field strength local exposure limit, which is averaged over 6 minutes. The solid red line is the limit for the electric field for the whole body 30-minute average. Similarly, these blue lines here are for the magnetic fields. Once you get above 30 megahertz, you can, instead of using the individual E and H fields, use a combined power field. So there is a limit there for the peak exposure. Now in this area here, there is a difference between ICNIRP 1998 and ICNIRP 2020, because this takes into account the peak field. On the 98, these lines just keep going all the way up here, and so you end up with much higher limits. Sorry. I've gone on one too many. I can't make it go. There it is. So what the calculator does is it has these limits built in. It calculates from the EIRP what the field strength will be at different positions, compares the two, and gives you a conservative estimate of a pass. So the actual calculator, which some of you may have seen on the Ofcom website, it is conservative, but basically you have to input the EIRP and you have to input the frequency, and it will then calculate the distances. What we've done is added to that a front sheet which allows you to choose the type of modulation, the band you're in, the power you're putting in, a factor for the mode, which is SSB process, so that's 50% for your averaging, how much time you talk in a 6-minute period, what your cable losses are, how long your cable is, what type of antenna you are using, what height it is, and it then feeds the peak or the average EIRP into the Ofcom calculator and feeds back the answer. So what you end up with is the answer coming back. In this case, it says the separation you need is 2 meters, but we put a warning on that by shading it in red, because 2 meters is less than the near field zone. So you have to be a bit more careful about interpreting your 2 meters. But because your antenna is 7 meters high, which is 5.2 meters above your head, by the time it gets down to your head, it's outside of the near field. So that particular configuration is compliant.
Yes, I've wondered about that, John, because the when they Ofcom first came out, it wasn't clear how they were measuring this separation distance. Now, my assumption was if you've got a high gain antenna up at 60 feet, for example, you're not going to have your neighbour or a member of public standing on a 60-foot ladder, and certainly not for 30 minutes at a time. And therefore, my assumption always was, but it was never clear, that these strengths essentially being measured at ground level, as it were, and therefore, by the time you've got a gain antenna at height, generally that shouldn't be a problem.
Agreed. The other thing that we've got in the calculator is this number here called side lobe loss. So if you know you're 60 dB down at the angle where the limit is, we'll let you put a loss in there and it will make your distances a bit more acceptable. So that's the basic calculator. I do go on to show you what we're using at the moment for separation distance. I should say this is not an exact, well, this is not an exact implementation of science anyway. The science may be exact, but it's not an exact implementation. But the aim is that if it gives the wrong answer, it gives the wrong answer that is protective of the general public. So it makes it a bit longer. So
John, the calculator that you're using, very early on, there was a calculator.
Lost your sound, David. You've muted. Can somebody?
Yeah, sorry. Yeah, sorry, John. Very early on in this, there was an ICNIRP calculator produced by DL9KCE, and I assume that your calculator is based on a similar kind of engine.
The ICNIRP calc is better because it takes into account many more antenna types than we do. We're actually built on the Ofcom engine for a very good reason, that we can't be held liable if the Ofcom engine gets the calculation wrong.
Yeah, understood.
But we are doing some more work. How much longer have I got, Michael? Can I go on for another 5 or 10 minutes? Or you're muted.
Sorry,
right?
sorry, John. Yes, I'm unmuted now. You've got plenty of time. I should be over in about half the time. No problem.
Okay, so what I wanted to do, I will demonstrate the calculator at the end and let you ask me any questions about it. But if we look at this particular diagram, then as David was just saying, what we're looking for is making sure that the person is outside of the zone where you might exceed the levels recommended. This is just one of the ways in which you could achieve compliance. So what we've tried to do, being a software engineer once upon a time, as David will remember, I decided what we needed was a flowchart. So if you start at the beginning, then the best way of doing it is screening by configuration. If you have a pre-assessed compliant configuration, you follow the recipe, you're there. And one simple thing would be, for example, for handhelds of say about 5 watts with their rubber duck on the top. If you can prove that the EIRP of your handheld is less than 10 watts, then you are inherently compliant. You don't need to do any more, providing you operate in that condition, except keep a record and stick it with your license. If you can't do, and there will be other types of pre-assessed compliances, you know, inverted V with the lowest point being 3.5 meters above the floor and the peak at 10 meters, and you know, as long as you stay out of these exclusion zones, then you will be compliant. So they can get more and more complicated as you go nearer and nearer the limits. But the important thing is that they're all about separation. They're trying to find out how far you need to stay away from the source in order not to exceed the EMF. If you can achieve that separation anywhere where people are, then you're normally compliant and you don't need to do any more except keep a record. If, however, you're pushing the limits, you may need to look more carefully at the exposure zones. You may need to put a fence up or a camera to keep people out of a couple of areas where you might exceed. If you do that and you can prove that people can't get in, or that you won't transmit if people do get in, then you can still be compliant. If that fails, then we've got some more complex modelling. We can suggest other mitigations you can try, and basically you keep going round the loop until you either give up or you're compliant. I have no non-compliant output to this flowchart. And once you've kept the record, job's done. If you any questions on the flowchart?
Well, just a question on record keeping. I assume that it's enough for us to keep records ourselves. In other words, we're not required to submit these records to Ofcom, but if Ofcom challenges us, that we must be able to produce them.
Correct.
Yeah.
And you must be operating to whatever configuration you put down. I didn't talk about it when I put the spreadsheet up, but you notice at the top there are a load of beige boxes which you basically fill in with your configuration and then keep a PDF or a printout, and that will do for you. But what I was going to do now is just to give you a flavour of the exciting modelling work that's going on. So there are a number of advanced methods. So if you can't work with the limitations of the simple tools, and they're aimed so that we hope the majority of amateurs who are using simple configurations will be very able, easy to prove that they are compliant without going to a lot of work. But because there are cases where work is needed, we've been very lucky. Some of you may know Peter Zollman. I don't know if David knows him or some of the others. He's one of the world experts on this topic. He's also a ham. And we've got Ian White, who I know many of you will know, who used to work for the Protection Agency. And we've got 3 guys in the States, the head of safety in ARRL, and 2 other guys who work with Peter on all the IEEE and European standards for this stuff. And they've been working with us to actually do the modelling and come up with some more complicated stuff. So a number of you are probably used to EasyNEC or ENEC. This is NEC 5, and this is a model of an antenna. What you see on it, 27.7 volts, is the 30-minute average limit line. So anywhere outside of that line is compliant at this particular configuration. Gets very hot in near where the antenna is. This is, I think it's an 8-element 2-meter Yagi. This is the height of the things above ground, and this is the distance on bore site. The interesting thing is that as soon as you put a person into the field, he actually focuses that field and can bring it up. Up here, where there's nothing interfering with the field, the limits are still there, but here we've got a gap. So you have to be careful that even putting a person in the field can cause problems. Now, this particular diagram that comes straight out of NEC 5 isn't easy to interpret. So what Peter's been doing, along with help from the others, is he's been integrating the energy over the body at different positions and comparing it with whichever is the worst of the two limits, and coming up with what we call a compliance contour. So now,
Sorry,
what
John, is that the diagram we just saw? That's just purely computation. Is that
Yep.
what we're looking at so far?
Yep.
Thank you.
That the one before, if I could go back to it, that's a model of the E field for a unit par, I think it is, put in, and showing you where the E field hits the two limits.
Gotcha. Thank you.
All right. Now what we're trying to do is to find a way of expressing that which is more useful to us, because what we need to know is not what the E field is, but where we absorb enough E field in order to exceed the limits, and that's what this diagram attempts to show.
John, can you tell us what sort of power level that's running?
I think the earlier, I can tell you exactly on this one. Can I answer it on this one? Because I don't want to go, but I think the other one's running at 1 watt, which is just a normalized power. But I don't know the answer. This one I do know, because what we've done now is we put in whichever is the worst of the E and H field, local or body average. And if you stay out of that zone for 10 watts, then you are compliant. Similarly, if I go to the other extreme, if you stay outside of that zone for 400 watts, then you are compliant. And this axis is where your foot is. So it's actually, if your foot's at 6 meters, it's integrating between 6 and 1.8 meters to get the total energy that goes into the body, and then working out the contours. So with
John, can I ask a question?
Yep.
There's this whole idea of a 6-minute compliance. So it averaged over 6 minutes. Now, as far as I can see, that the problem is that from my point of view, say in an average hour, I might only transmit for 6 minutes. And so am I allowed to say, well, actually, I'm only transmitting one of those 6 minutes, for example, or, reduce it in proportion to say,
yes,
you are.
providing you're above 10 megahertz. Below 10 megahertz, it's a peak measurement that's your limit. I'll explain that when I demonstrate the calculator.
Okay, go for it.
Just one very quick question.
Yep.
On the question of, say, a G5RV, do you take the feed point into the top of it at the T, or the feed point at the base of the ladder line?
We suggest you take it at the top. The answer is, if you're going to get exact, it's the nearest point to you is the point that you need to be calculating from.
Yeah, because mine's fed from the ground just about, so it's a very low one. Okay, thanks.
So what I was going to ask you was, if you were to write up what this means, what would you write?
The higher the antenna, the better.
That's true. But for this particular height, which I think is 8 meters, what can you write?
You're safe providing you're not more than 2 meters tall.
Correct. You are safe everywhere at ground level. All right. So what we hope to do is not to publish these for every amateur to try and understand, but what we want to do is to work out configurations where you are safe. I mean, if you dropped it a bit, you can imagine that the whole picture would just come down a little bit. It distorts the closer you get to ground, which is one of the interesting problems. So if you drop it by 1 meter, you may find that this bit here actually drops by 1.5 meters because of ground interaction. But what we want to do is to come up with a configuration like this and say that anywhere at ground level you're safe, at first floor height or at the worst point on a building, providing you stay 18 meters away, you're safe. You're compliant. That's the sort of advice that we want to come up with in our pre-compliant configurations. And in order to do that, I mean, we have been working on the E and the H fields around dipoles or doublets, depending on what you call them. And here it's normalized to a watt again, but you can see how the fields change. This one at the top here is a dipole. That's what the E field looks like, and the H field. As soon as you make it into an inverted V, the area on the ground that is affected gets smaller, but the signal strength increases, so you have to start to avoid. So it's all that type of work that we're trying to put into a number of compliant configurations. So, any questions for me?
Yes. Can I ask a question?
I'm sure you could ask it. It's whether I
Go
can
ahead,
answer
Ben.
it or not.
Yeah, you mentioned wire antennas, which aren't necessarily horizontal. Parts of them can be lower down, and we'll take the inverted V as the example which you gave, where you're feeding it at the top, and it slopes down, let's say, to 2 meters off the ground, i.e. it's tied to a convenient fence. Now,
then we would advise you not to do that because it can be touched.
agreed. All right, let's say it's
3.5.
The inverted V is in such a way that the ends can't be touched, but they're still not very far from head for height. Now, we all know that hopefully the feed point has the highest radiation and the end points don't. Is
Wrong.
there an allowance for this, or am I wrong?
Yeah, well, what you have to do is you have to meet not the power, you have to meet both the E and the H field. So strictly for a doublet, the maximum current is in the middle, which means the maximum magnetic field is in the middle, the H field, but the maximum voltage is on the ends, which means the maximum E field is on the ends.
Yeah, I understand.
What this calculator does is it calculates the E and the H, compares them with the limits, and if either of them don't meet the limits, then the whole thing doesn't meet the limits. Then it calculates the separation, which is the shortest distance at which all of the limits will not be exceeded.
Okay, so an inverted V fed at the middle, up high, well above head height, doesn't necessarily mean it's automatically compliant.
Well, I think it depends on the band, but if we look at, this is actually, well, it's a ZS6 BKW, but it is a doublet. It's a G5RV on steroids, if you don't know what it is.
I know the antenna.
At 7 meters, I'm running on the calculator now as opposed to the slideshow, then the Ofcom separation comes out at 2 meters. Because 2 meters is less than 3.4 meters, which is the near field limit, lambda on 2 pi, then we give you a bit of a red warning and say don't just assume compliance. The next thing we do is, because the near field limit is less than the vertical separation, it doesn't matter whether it's 2 meters or 3.4 meters, because the field strength at body height for the ground is compliant. So the horizontal separation needed is 0 meters, which again means that providing you're not more than, I think this is 1.8 meters tall in this case, you will meet compliance everywhere, but we expect there to be another caveat on there, providing the ends are more than 3.5 meters high, or more than 3 meters high. that's the sort of thing we're looking for. It gets complicated, as I said, because if you put in the Ofcom calculator doesn't take into account the need for peak limits, which is in the ICNIRP 20. So we're working with them at the moment because at some stage they've got to change over to ICNIRP 2020. But the sort of problem you have, if I go to 80 meters, the gain won't be right because it's a single frequency gain for these antennas at the moment. We've got to put in the variable frequency. Yeah. But here what you see is that it's now saying 1.3 meter separation, but 13 meters near field. And what we're working on at the moment is, rather than give you an answer that's impossible, we're trying to find a different calculation to do when you're in the near field that will show you compliance.
Thank you.
Presumably, John, if you're using a doublet and you're using it on a frequency higher than the lowest frequency for the doublet, the radiation pattern is going to be multi-lobed. So presumably what people will need to do is to go to something like EasyNet or something similar, or Mananagal or something, and actually just look at what the peak gain is on those lobes.
Well, what we hope to do is to produce those compliance contours for them to avoid them having to do that.
Oh, okay.
Yeah, I mean, yes, you can do it that way, although we've had to go to NEC 5 to get reliable answers. EasyNet and Mananagal don't work for this. Right. The errors in approximations are too big. We also, I mean, when we run these calculations, we run them every meter in X and Y space and every 1/10 of a meter in height, because we're integrating over the body. So it's all run by, there's a Mathematica program that generates the grid, runs the calculation at every spot distance and every spot frequency, calculates it all up and comes up with the compliance contour answer. So it takes half an hour to run on a pretty powerful computer for each configuration.
Question from me, G3XYX.
Go on then.
My station doesn't feeds a long wire down the garden. So we go out the shack window from the ATU for about 5-10 meters, up an oak tree, then a big span across the top of the house and the back right the way down to the back of the garden. It's well above head height, it's at gutter height plus. I would say that is impossible to calculate, and one would have to have a field strength meter during operation to make sure that I'm within limits. Is that a correct assumption with a long wire antenna, end-fed, tuned against ground?
Well, I would not accept that anything is impossible to simulate, because NEC 5 and some of the other modelling programs, and there are even bigger ones, can do a very good job. It might be difficult for an amateur to do it. The other way of doing that, of course, is to go out on balance feeder, go through an ATU and then use your long wire. And because you can put your ATU where people can't get at it, then you will easily be compliant with what you said. The difficulty is where you go out, if any members of your family or visiting friends can get close to the wire.
ATU is next door to the transmitter in the shack.
I'm not going to say anything because I'm an EMC man as well, and that is bringing RF in the shack.
I have the same problem, but in my case, my garden is extremely short, and I've got a diagonal bit, 155-foot wire straight down the garden. The rest of the 105-foot goes diagonally across the garden, almost down to the ground, at a place where no one goes to. There's houses opposite. The exact distance the house is, I don't know. There's trees between me and them, and a ditch. And it's going to be damn near impossible to measure anything.
Do you mean calculate or measure?
Well, calculate, I think.
There will be some configurations that are difficult, but the calculator, the simple calculator, if you apply it, will, once it's finished, I'm not saying that this second it does this, but it will not give you an unsafe answer. It may give you an answer that you're not compliant and you need to do something about it, but it won't give, but you can see from the sort of numbers that are coming out here with quite sensible things, you know, a few meters away is fine. I shouldn't be using 80 meters because, well, I can use 80 meters. To allow me to do this at the moment, I've got a little toggle here. So if I go to peak EIRP, then that is what you need to use at 80 meters. The limit's slightly wrong on the calculator, but you know, you're talking less than 5 meters for 100 watts into a ZS6 BKW. Now your long wire will have a lot less gain than that. So that once I put in,
most people's gardens are quite a lot less than that wide.
Exactly.
Yeah.
I mean, my garden is quite close to the neighbours, both sides, and the garden at the bottom of the garden.
But if your antenna's high, then you're getting the separation also from the height.
correct.
Well, I can go no more than 35 foot, really.
Well, 35 foot is say 10 meters. So if I put this up at 10 meters, then with a vertical separation of 8.2 meters, which is 10 minus 1.8, that's a hard bit of maths, isn't it? And distances coming out around 10 meters, you're likely to be compliant. And that's with a long wire.
So, John, you did mention that below 20 meters there was something weird going on. Could you explain what that was?
Below 10 megahertz, maybe?
No, you said below 20 meters.
Oh, 10 megs. I think John said 10 megs.
Did he? Okay, I apologize.
Yeah,
I thought
it's actually on the spreadsheet.
Yeah. No, what happens below 10 megahertz is that the predominant effect of a human body is what's called electrostimulation. In other words, it makes your nerves tingle. And that is a peak effect. So what you have to do is you have to run the calculator using peak EIRP, which is 367 watts, instead of average EIRP, which is a quarter of that.
Okay, so I'm back to that question of the duty cycle that I asked earlier, which is where.
Well, what do you want? What duty cycle do you want?
Well, that's exactly my point. That you know, in an average. So here's a good example. Tonight I operated on 20 meters FT8. For about an hour and a half, but it's the first time I've been on in 2 weeks. So am I allowed to say, okay, FT8 at the worst case is a 50% duty cycle because I'm transmitting for 50% of the time. In practice, I'm transmitting far less than that. You know, maybe 20% or 10% of the time, because it's only those stations that I'm calling. I'm not endlessly calling CQ or whatever.
The problem is if a person is there when you're transmitting for 6 minutes, he's going to get hot.
Yeah, but it depends how long they're there for, and then what length do we determine that duty cycle over? Now you said that
6 minutes.
Fine, but you could have taken 6 minutes yesterday, and I wasn't on yesterday.
So you didn't have a problem yesterday.
Don't you have to show compliance in your worst case operating scenario, Russell?
Do you?
So, well,
isn't it?
If you could be transmitting for FT8 for a 6 minute period, then you have to assume 50% duty cycle. That's the worst case it could be. And if you're compliant at 50% duty cycle, well, you know, then anything else lower than that is perfectly fine.
But if you transmit for 6 minutes, then you have to put 100 in there because your mode factor is the line above.
Well, you don't, because in FT8 it's 50%.
Okay, well, I don't use.
You transmit and then you receive, and then transmit and then receive.
So you are transmitting half the time.
Yes.
In fact, FT8 is not half the time transmitting, is it? Because it actually finishes quick in about 13
Yeah, so
seconds.
it's a little less.
Yeah.
Yeah, Bill could answer that. But I think it's about 40% or something rather than 50%.
Hello, John.
Hi, I've got it wrong because it says 100%.
Well, it isn't. Yeah.
No,
John, this is Mike. I'm just wondering, are you able to stay on until after I do my presentation so we can have a question session at the end?
Yeah, I was going to suggest that you chat now, and I'll come back to the calculator at the end, if that's all right.
Okay, that's super. I'll try and whiz through my presentation, and
sorry I took so long.
Thank you.
Mike, sorry, just before you start, can I ask John one quick question, which is rather more general than all these specific ones, because I may have to go.
Go ahead, Bill.
Yes. Yeah, thanks, John. Just a quick question. You confused me slightly. Am I correct in thinking that you are taking the worst of the E and H field separations and just showing a single separation without saying whether it's E or H field?
Correct.
Okay, so people with wire antennas, that's not helpful, is it?
Why?
Well, because as you pointed out, the E field could be at the ends, and if they're getting a separation for the H field, it could be irrelevant if it's 40 feet up in the air.
Yeah, what we've done to try and help that is we've said that it's from the nearest point on the antenna for big antennas.
Okay, yeah, okay. Well, on lower frequencies, again, I think that's unhelpful. But okay, let's.
I mean,
thanks.
The problem we've got is that in order to be exact, we have to do the complicated maths, which most people can't do for themselves, and we don't have the resources to do. So the simple calculator isn't accurate, but it is on the side of safety.
Yeah, fully understand, but it could be quite a big.
I believe that when Ofcom bring out their next version of the calculator, they're going to put some limits on the configurations that it applies to, and it's going to mean that for 40 meters and longer wavelengths, we're going to have a different calculator. But I'm waiting to see what they do. People in their replies have worried them about the sort of things you're talking about, so they're now making their calculator applicable in less frequencies.
Okay, thank you. All right, sorry about that, Mike. Carry on.
Thank you, Bill. Can somebody just confirm that they can hear me?
Yes.
Okay, thank you.
Yeah.
Right, I'm going to talk about measurement, which John has already said is really hard to get right, and I accept that. But I thought I'd have a little play to see whether it was possible or not, and this is the result of what I've achieved so far. It's a work in progress rather than complete. So here we go. First, items continued, being concluded rather. I'll first start with other possible analysis methods. I've in the past used VK3UM's EMR program. Unfortunately, he's not with us anymore. It was a very highly respected calculator, and he's used it for EME work, I believe, and he had his station investigated by the Australian Regulatory Authority, and so I think you can say that this program is useful to check other models by, because it's been used so much, but we can't see it being maintained into the future. Other modeling tools, I think where a custom antenna, various funny shapes, a lot of amateurs use funny shaped antennas. I know I do. and it comes near to a property boundary where there could be other people near to it, where there's a little ground clutter. Well, there is not much ground clutter and ground conditions can be estimated well. It could be used. There are various models available to amateurs, MMANA Basic and others, and those are free, but unfortunately they're not too accurate. Whether they're accurate enough, I don't know. NEC 4 and NEC 5 tools are high cost, and possibly even, I don't think you can buy NEC 5, can you, John? Perhaps you'd answer that later. I know we can get access to it as RSGB, but I'm not sure an individual can get access to it. Right, so why bother with testing? It went through my head that if the calculator doesn't show a compliant system, it may be of use to find out what's going on, and then make action to change the system to make it compliant. Perhaps commission some better analysis to determine whether the system is possibly usable as it is. Analysis cannot easily take account of all conditions, whereas I believe that measurement could be if it were accurate enough. And I think the accuracy requirements are quite stringent. That's the problem. Also, if the station is near to the limit, it may be useful to support the calculation with testing evidence to prove that the system is compliant. When I say the system, I mean the amateur radio station. I've just covered all of that, I think. Right. Any commercial test equipment is likely to be prohibitively expensive, and by that I mean several £1000s. Even for clubs, that's too much. Most low-cost commercially available meters should, as John said, view them with great suspicion because they're probably not very much use. I'll come to that a bit later. Homebrew approaches, I believe, can be used with care. And one of the things about the low-cost commercially available meters is they're wide band generally, diodes with antennas connected to them generally. And I believe that a spectrum analyzer or SDR at a minimum is what is needed. But there are some really very low cost spectrum analyzers that may be suitable, such as the Tiny SA. £50 worth. It's not bad, is it? Okay. Right. I'm not going to dwell on the maths, but the first one is, imagine a sphere. The power is transmitted from the center of the sphere. The power density in watts per square meter, which is one of the measures on the that we're coming to, is just basically the power divided by the area of the sphere at the radius of interest. Now, there are some equations for an isotropic antenna which you can't make, and a dipole which you can make, which tells you what power you get out of it from a matched antenna based on the wavelength, the power density we just calculated, and 4π. Knowing the gain of that antenna, you can work out overall what the loss is between two antennas, and I'm coming to that later. I keep saying that, don't I? Right, look at the right-hand side. Here I'm showing for the first time, if I can get can I get my, no, I can't get my pointer to go onto, oh yes I can. Right, the electric field here is shown as vertical. The magnetic field is shown as horizontal, and E cross H, which is called the vector cross product of the two, is the power flow. So the signals flowing, or the power's flowing in that direction with the electromagnetic field in a transverse manner, and that's called a transverse electromagnetic field. And these equations on the left-hand side, for example, the electric field is E in volts per meter, is calculated by eta times the magnetic field, where eta is 120 pi, or in other words, 377 ohms. And it's a bit of a strange impedance, but it's the intrinsic impedance of free space. Right, I think we'll leave the maths behind largely. So this is the controversial slide on far and near fields. And I heard the figure lambda over 2 pi mentioned earlier, which doesn't seem to come on this slide because I haven't taken account of the boundary between what is known as the reactive near field and the radiative near field. Perhaps we could talk about this a bit later, John. Why are we using the reactive near field as the limit of the near field? Because the equation where the antenna is a long one, not a dipole, but a multi-element beam, is 2d squared over lambda, which for 2 meters, a long 2-meter beam could be up to 16 meters. So it's possible that even at VHF, you could be in the near field for a long way. Right, measuring at VHF stroke UHF. I'm just going to have to keep an eye on the time, I think. Just make sure oh yes, I'm okay for time. I said VHF and UHF distances are generally in the far field. I think we could safely say that where we're talking about EMF to the neighbour's property and neighbour's people. Certainly in the case of simple dipoles, you can be sure you're in a far field. What I've done is I made a couple of simple dipoles at 432 megahertz. I've also made a 2 meter one, and I've used it to see whether I can correlate the measurement of the field from my 432 megahertz antenna with the predicted field using the pattern of the antenna. And here we go. So the first thing to do was to calibrate the 2 dipoles. What I did was I connected the 2 dipoles via 2 feeders to the spectrum analyzer with tracking generator, and I put them on tripods, moved them apart, measured the distance with the laser distance measuring device, and did 4 calculations on a spreadsheet to try and calibrate them. And the measured calibration factor, that's the nominal gain of the dipole relative to isotrope. This includes the feeder loss and everything, mismatch loss, because of course a dipole is 75 ohms rather than 50 ohms. Whereas the expected calibration factor would be 0.733 dBs. So they're a bit different, but at least I calibrated them based on the fact there were 2 identical dipoles, and that gave me a baseline of what the performance of that dipole and feeder was. Note that here I'm using different distances to separate them by, and I'm getting different values of measured loss from the calculated free space isotropic loss, giving these differences in dBs, getting some strange results, but that's largely due to ground reflections. I think with hindsight, I would try and make a better test site with fewer ground reflections, but I've changed that to power, averaged it, and worked out a calibration factor. It needs a bit of work, but it's getting there. Right, that's the dipole inside my shack connected to the spectrum analyzer.
Just a question about the setup there. So presumably using the tracking generator or something like that off your spectrum analyzer.
Yes, on that one, yeah. I'm using the tracking generator and the spectrum analyzer to measure the loss between the dipoles.
So that your tracking generator is just barefoot.
Yeah, that's
cool.
Right.
Thank you.
On the actual testing setup, this is a 1.5 meter high pole next to the spectrum analyzer down in the shack where I am now. This shack has got a fairly open roof. It's only tiles and felt above me before it sees the beam outside. So there's very little loss through that. Oops. That's the transmitting antenna, and the 70 SEMS beam is about 7.5 meters above ground. And the antenna data I used is from the website. I was going to show you a plot of it, but I realized I'm not allowed to by copyright law. So there's the link. And then we come to the next one, which is the first one is the measurement. And I calculated what the receive power is and the receive power flux density in watts per square meter. That's going back to S basically, right? And compared that one with the calculated one using the ball site gain, the side lobe loss taken off the graphs, the feeder loss calculated, and there we are, 0.46 dBs difference between the two. I think that's a fluke, but we'll see. It's encouraging, put it that way. I thought, well, just let's try it again. This shows both of those two dipoles, and it's measuring minus 3.2 dBm. Go back to the spreadsheet, and months ago, I was, where are we? Measure power, minus 3.65. So I'm different by 0.45 dBs over several months of time, running 75 watts into my 20 element beam. So it's not changed much. Okay, on to HF. For HF, you can use small probes, which you can purchase online or make yourself, that can either be sensitive to E field or H field, and connected to a spectrum analyzer, even the cheap one would do. However, getting them calibrated is a bit of a problem. So what I've done is built what's called a TEM cell, and I'll show you that in a minute. You need to use both types of probes because of antennas, as we discussed earlier, do have different readings of E field and H field depending on which part of the antenna you're talking about. And as I did on the VHF, I forgot to mention this, just move the probe around to get a maximum reading. I use CW to test this, and use a peak measurement on the spectrum analyzer, and it just records the maximum value seen on that frequency. Oops. Right, TEM cell. This is basically an expanded transmission line with a septum in the middle, which is the inner of the coax essentially, and can be used. It's the distance between this earth point here and the septum, in my case, is 100 millimeters. So you've got enough room to put in a probe, and on the spectrum analyzer, measure the output from the probe with frequency given a known field strength. The old E field and H field shown again. And this thing's designed to be matched across its whole length, so into 50 ohm load. Okay. And it's designed to have a line characteristic impedance of 50 ohms, not to be confused with the intrinsic impedance of free space, and with excellent return loss and VSWR. E and H fields in the TEM cell have got the same relationship as in the far field, in other words, related by eta, the 120 pi 377 ohm figure.
Mike, sorry,
yeah?
Quick question. I thought that for transmission lines that the separation between the conductors actually affected the characteristic impedance. So when in your sort of configuration where the earth part actually widens and separates out from the inner, doesn't that increase the characteristic impedance at that point? How can that possibly be a constant 50 ohm impedance along its entire length?
You just widen the strip. So I'll show you this in a minute. It's quite interesting to see it. Just going through to the electric field, you can calculate from the known voltage on the inner of the TEM cell, and the distance d, which is 0.1 meters. So for example, you can get 7 volts per meter for 10 milliwatts applied power, which is quite a lot. It's a bit more than the capability of the spectrum analyzer, but a signal generator or a rig would do that quite easily. This thing can take quite a lot of power, a few watts of power. Right, that's it. I spent quite a few hours building this thing. On the left-hand side here is a connection to my directional coupler box. You can just see it on the left there, the spectrum analyzer there. And on the right-hand side, you can't see it, but there's a 50 ohm N-type load. And this is a widened strip line. It's designed for 50 ohms. It widens out, goes along, and then narrows back down again. And between these two, you can put test samples in to be measured. And these things holding it together are PTFE rod. As you may recall, on Discord, I was asking for some PTFE rod a few weeks ago, but nobody had any, so I bought some. Okay, and this is the result of the return loss measurement. The yellow trace is the actual directional coupler I'm using. It's a homebrew one, so it doesn't get better than 20 dBs over the low end of the band. But the TAM cell, apart from that little peak there, which needs investigating, is better. So we could say roughly we're getting 20 dB return loss in the low VHF area. So I'm confident it's working, and it's certainly, if you look at it, it's not built properly yet. I haven't soldered these joints together properly, and there's quite a bit of tidying up work to do to it. It needs a clean up. So it's there, nearly. Right.
That's just PCB material, presumably, you've used?
Yeah, that's just some old copper clad that I had lying around. And I've put inside this. This is...
That thing that you've just showed us, how does that work
in
terms of practical?
What you do is you feed power into this side through to the load at this side, and it's just like a piece of coax, but instead of not being get-atable, you can actually put things inside this. So if you know how to calculate the field within that, I suppose I forgot to say it's called Project TARDIS. And the reason why it's a TARDIS is it behaves like free space.
Yeah.
When you walk inside the TARDIS, it opens out to massive amount of room. And basically, this is acting like a free space transmission. And in fact, TEM cells are regarded as nearly as accurate at open air test systems, but with the advantage you can have them in your shack and keep in the dry. So you can put a probe in here and it will act as though it's in an electric and magnetic field. And the electric field is basically the voltage across that divided by the distance 0.1 meter between them.
So is this an accurate model of what might be going on in your back garden?
Exactly. I've done a lot of research into this, and these are several £100s to buy even inferior models to what this seems to be. There's a company called TechBox which make them, and they give the performance figures, and they're not up to the ones I've seen so far with this one. So I'm hoping to improve this. So I'm really quite pleased with it. Okay. That's the result of that. This is a field strength meter, not so cheap, by the way, but it's on loan from RS Components, and they've asked me to review it for them, and I've struggled to review it so far. But now I've got the TEM cell. It's actually proving to be much better than I thought. The field strength in the TEM cell was 2.2 volts per meter, and it's measuring 2.899. So it's not too bad. More to come on that one. And finally, this is a bit of a tongue-in-cheek thing, but I'd like you to comment, John, on how feasible this might be with Ofcom. A Raspberry Pi box, a processor in other words, taking in rotator azimuth data, RS232 or the like, and also from the power amplifier, a power meter within the power amplifier feeding out digital power level over time, integrating in the Raspberry Pi over the 6 minutes, the last 6 minutes, and producing an alarm when any point that the antenna's pointing at receives greater than its 50% of its allowable limit of power. So throughout a contest, for example, you're rotating the beam all of the time. Could this be used to control the amateur's EMF exposure to people? Please note this approach is not yet approved by Ofcom because I don't think they've heard of it yet. I've only just told you. The Raspberry Pi monitors the operation of the station in real time, stores the EMF for each sector of azimuth, each 1 degree, reads instantaneous power from the power meter every 100 milliseconds, integrates the power over the last 6 minutes, and from the antenna elevation pattern and property boundary knowledge, works out EMF and warns when it exceeds the threshold, such as I mentioned, 50%. The operator can then take evasive action. A bit of a tongue-in-cheek, but it might work. Okay.
I can't imagine it being terribly popular with contesters. If you're contesting, you want to be focusing contesting, not worrying about, oh, I've got to point the beam away from where I need to in order not to exceed my my 6 minute threshold.
I think the point, David, is you're not going to be pointing in one direction for 6 minutes, as far as I can tell, on a contest.
Depends very much on the contest.
If
you're working all Asia, for example, you're going to spend most of your time pointing within about a 30-degree sector. Anyway.
Yeah. Well, you may be quite right. Yes, it's just an idea. Okay, that's the end of my presentation. Apart from a summary, so I'm going to say that for simple low power stations, yes, the calculator will suffice. For well-characterized stations at VHF and above, an analysis should be possible, particularly if you can get your antenna high enough. But where significant unknowns are present, such as trees, ad hoc wire antennas, fences, buildings, etc., measurements may have a place. Right, that's Mike Naylor, CDF's view. I look forward to comments. Thank you very much.
Just before we start to open up the questions, as I'm sure there's going to be a vast amount of, I would just like to say a very big thank you to both John Rogers and Mike for the brilliant talk, and just give them a RADARC clap there before we go over to questions. So well done both, and thank you very much appreciated.
Thank you.
I need a recording of applause, because one thing that Zoom doesn't do very well is the sound of people clapping. Anyway, over to the questions there, everyone, and who's got some questions?
Could I ask John something?
Yeah, go ahead, George.
Yes, I mean, I had the impression that the original, certainly the original Ofcom calculator, didn't seem to be taking near fields into account at all. And I mean, one of the problems to me that strikes me is that while far fields are not that hard to sort of calculate in general, near fields are very unpredictable and difficult. I don't as yet have a feel for just how in practice with sort of real antennas, the near fields tend to sort of work out. It would seem to me that the ideal thing here is to try and sort of get together a kind of rule of thumb or something that gives a sort of feel for it, because you know it's not obvious to me whether the near field values are sort of wildly more than the far fields if you scale the distances, as it were, or what. And I've looked up sort of research papers on how you calculate this stuff, and it seems to be extremely difficult. And indeed, it almost seems to be some controversies about exactly how you go about it as well, which just makes the whole thing rather hard. So, yeah, can you comment on this whole near field issue?
Well, the near field is an explanation of, I like to think of any point which has got an accelerating electron as radiating through fields. A reactive near field, which falls off as the 6th power of distance, radiative near field, which falls off as the 4th power of distance, and a far field, which is the normal inverse square that we're all used to. Now, what that means is that if you do the calculation using the far field calculator and assuming no ground reflections, then it will always give a very conservative answer, because inverse square is always going to be much further away than inverse 6th. And that's why, by the way, we use lambda over 2 pi, because the most significant region is the reactive near field. Unfortunately, when you put conductors into the field, they distort the field, and you can't have a simple formula in the near field.
No, appreciate that. But my concern is that the near fields are actually have the potential for being quite extreme, you know, at the places where they're really high, and that these could actually be dominant, especially for HF, where the wavelength is really large, probably bigger than the garden. So really, the whole thing is about near fields, and this is seems to be a really difficult thing to get a handle on.
Which is exactly why we've gone to the diagram which I'm sharing, because I don't mention any type of fields there, near, far, or anything, because this is the actual value of the field strength worked out properly. This one uses the method of moments, but it is a very accurate model of what the field strength would be. And one of the things that we plan to do, as I said, perhaps with Michael's help, is to set up some examples. This is a 2 meter 8 element Yagi, and actually go and do the measurements and see how accurate this model is. But we're only going to do the measurements on the boundaries, so we most certainly won't do 400 watts.
Yeah. The problem with this, of course, is that these types of calculations are very artificial compared to something like an HF aerial in a garden. My garden would be a wonderful example. There's great big wire fences which act as sort of huge reflectors and things, and so you've got real big problems, and so you need to be careful about where your sort of extreme fields actually are. It seems to me it's an absolute minefield. I mean, I've been sort of part-time EMC engineer ever since the CE marking stuff came in, so I'm well familiar with the sort of measurements. But of course, we do all that at higher frequencies typically. I've been looking at techniques for doing this with HF. I haven't. I've been adopting a different approach with this in terms of measurement techniques to see if it's possible to do to get reliable results from. You know, certain structures have predictable properties for measuring, and this is in fact how you sort of calibrate the things in the first place. But I've also rather lucky, and I've got an original GPO measuring field measuring receiver, an antenna system, which as used by the GPO back in the day for specifically for HF. So I'm just getting that up to spec. It's self-calibrating, which is rather useful. So it'll be interesting to sort of see how things go. But my own experience in the EMC field is that the actuality, especially when you've got, you know, sort of things near aerials and bits of fences and wires and goodness knows what hanging around, the distortions you're going to get from that are terrible. And so you've really got to come up with something that sort of estimates how bad it could be and puts in enough of a margin. I don't think it's safe to sort of go up to the limits on this to calculate precisely what it would do, because sure as hell it won't do that. And as you say, the measurements, these things are going to be quite difficult.
Well, let's tackle a couple of those points first. Let's look at measurements. In order, I suspect, I mean, Ofcom are not going to be able to check every single configuration of homebrew that an amateur comes up with and calibrate it. So what they're going to do, and they've done this to some extent in their first paper, is they're going to say you must follow a measurement procedure, and the one they recommend is K52. And there is a procedure for doing that. So if you want to take measurements and you want to prove they're compliant, you're going to have to do it to a documented procedure. It might be an IEC procedure, it might be an IEEE procedure, it might be the existing K52 procedure that they reference in their first consultation. And why will they do that? Because they don't have the time to come out and check that the method that you've used to make your measurements, or the calculator that you've thought up when you woke up this morning, is actually going to give the right answers. So what they're going to say is either you have to use an approved calculator, or you have to use an approved measurement procedure.
Oh yeah, I mean, because they're not actually going to measure anyone at all, I would suggest. I don't think it's going to happen ever.
I didn't say they had to use it. I said you.
No, yes, quite. I mean, they will simply want to see your piece of paper, of course.
Yeah.
And until a neighbour gets fried, in which case they will validate your piece of paper.
Has that ever happened?
How would they know that a neighbour got fried?
Well, they haven't so far.
Exactly.
And
So I suspect this would only ever come into account 30, 40 years in the future, where someone says, oh, I got cancer because there was a radio amateur who lived next door to me 30 years ago.
Funny you should say that, because at a contest like we use for VHF, it happens to be next door to somebody who bought essentially a house that owned to the farmer that owned the field, and he claims that that the few weekends that field is used was related to cancer. We have to point out the fact that there's a difference between ionizing and non-ionizing radiation, and there is no medical evidence whatsoever that cancer can be caused by non-ionizing radiation.
No, David, the cancer was probably caused by the exhaust from your generator.
Yeah.
I think that's a more likely explanation, George. I'd agree.
Yeah.
Okay, if I can come back and answer your question again. No, I guess the only guidance we've got is how many times have they prosecuted contesters for using more than 400 watts.
Yeah. One thing I get a bit upset about with all this, when I worked at Vodafone, I used to be in charge of the paging network, and I had to work out all the EMC issues and power radiated calculations for every site, and present these to Ofcom. And we wouldn't let any of our engineers do it. There was only about 3 of us we would entrust to do it. And we're doing similar things now and expected every amateur to do this. This is ridiculous. Yeah. That's my opinion. But we've got it, and we're going to have to do it. But we wouldn't even have let our professional engineers do it.
I think
so
I think John has summed this up in saying, though, that actually Ofcom don't have the resources and they can't be bothered to come out. So if you present something which is even half reasonable as a calculation, that's it. Then that you've done your due diligence.
Exactly. I think there's a danger that we're trying to overcomplicate this.
I'd always viewed this regulation as a whole, as a bureaucratic documentation issue.
It's a tick box.
The thing of all is not to measure the field or even to know what it is or even to know whether anyone's exposed. The most important thing is to have the piece of paper formatted correctly and saying the right things. That's way more important than actually it being safe, which is
it's a tick box paper.
I think it is exactly that, but it's also the caveat to say, actually, if you do this calculation and it says, for example, that the area underneath your 20-meter vertical is unsafe when you're transmitting at 400 watts, then you ensure that actually people don't go there when you're transmitting. That's it.
Can you do that? I have
your garden. You stop your kids going there.
The next door
you can do the inverse, and you can make sure that if somebody is there, you stop transmitting.
Yeah, but for example, John, my next door neighbour's house is about 7 meters away from my beam. Okay, if I have it at the lowest possible level and I point it in their direction and somebody were in their attic, then they would be irradiated at above the limits. If I put my power up.
So there you have a problem.
No, I don't, because I just
you don't have a problem. You just don't transmit. Yeah, you put the mast up.
Yeah, put the mast up higher. That's all I do. Yeah,
John.
What you do in your antenna field is to say the antenna will not be used for transmitting unless the height is X.
Exactly, but the thing I would say is I'm lucky. I've got well-characterized beams. They're from a manufacturer that publishes highly detailed data on those beams. I'm thinking, what about somebody who's got a beam that's been up there 20 years, perhaps one of the old J beams or something? You have no idea what its performance is. How do you deal with that situation?
Do you think it's going to radiate more or less than your good beam?
No, it'll radiate more because it'll have poorer side lobes, for example.
Will it?
John, can I ask you a question about microwave operation? Just something practical. For those of us who are using QO100 and running a couple of watts, which into an 80 centimeter dish can generate in excess of an ERP of 200 watts. I mean, will we be able to model these things? Because there I see some practical challenges, for experimentation when you're, maybe wanting to move from sideband to the narrowband modes up to the wideband modes where I might be running 80 watts. So what is that? I might be running 80 watts. I don't know. What's that?
But you're pointing up at the satellite loss. So
yeah, but
you're going to be off axis at ground level.
Yeah, but Dave, I want to know what I need to do, and will it be in this model, and can I easily model it?
It won't be in this model because.
There I go. There you go, Dave. It won't be in this model. What do I do?
Use a model that it is in.
Right. Okay.
What we expect that around half of people's configurations will be covered by this very simple spreadsheet. And because you have to fill in your name, your call sign, the date, the station, and any other details, all you actually need to do is to print that or PDF it, and the job's done. So for all of the people that works for, I can't think of anything simpler to do. We've also put in all the fiddle factors that give you the most chance of being compliant.
Yes. Okay.
So I think that's good. But to do the other detailed stuff, you're going to either need to use a finite element analysis or a method of moments analysis. And so far, we've spent a lot of time comparing them all. And
Yeah.
we for all of the soil types, we think NEC 5 is giving us the best results. We do have 4 people who've got it straight from the licenses from Lawrence Livermore, to ask an earlier question, and you have to have a valid reason for needing it. But as these 4 people are working out the standards for the IEEE and the IEC in how to specify and measure EMF fields, they are supplied it free of charge. Because they're the guys who are actually, and one of them, George, was it George that said he worked for Vodafone?
No.
Oh, sorry, who was talking and said they worked for Vodafone?
I
was going to ask, oh, that's right, it's G3. Do you remember that?
I used to work
Peter
for Vodafone, but there is a George who does calculations for Vodafone at the moment.
Yeah, well, Peter Zollman was the chief engineer who did them before.
I knew Peter.
That's what I was going to ask. I thought you would.
Yeah, it was in a different.
Break in, please.
Department.
Go ahead, Graham.
G3XYX1, has there ever been any sort of medical survey on staff who worked at high power transmitter sites in relation to health? Point 1. Point 2, everything so far is for a fixed installation, bar a beam which moves round. But what about our 5/8 2-meter whip in the middle of the roof with a small 70-centimeter aerial also on the roof when you're doing rebro on a Raynet supported fun run?
But there's until you said the last bit, I would have found it quite difficult to answer that question. But operating for safety allows you to temporarily avoid the restrictions.
Our good friends on RNLI and Mountain Rescue, hopefully, who brought that about. Thank you very much indeed. That's the first clear guidance I've seen, but that's very gratifying. Thank you very much.
For emergency services and stuff, if you look at it, it does say that you don't have to apply if you're saving lives because the risks are very low. The other thing that, 2 other things that, I mean, the car one is a case that's very difficult. The handheld at more than 5 watts is a case that's very difficult. But the other 2 that people haven't mentioned yet that give us the most grease are ground quarter waves or ground plane antennas, because the distance from the bottom is the peak point of radiation, and the distances can be quite large. And the other one that gives us grease is small loop antennas, because the E fields on those are phenomenal.
John,
this is build the loop.
John, survey transmitter engineers.
Sorry, somebody's trying to ask me a question. But
John, I have a question about the gamma equals 0.6 ground reflection coefficient. Yep. That doesn't seem to be applicable where you're using a Yagi, for example, a directional antenna. Why has it been hard-coded into Ofcom's model and not be able to be replaced by something more appropriate?
The people who are experts at this tell me that when they're doing it, that is the worst reasonable case. 1.6 is a reflection, and then it's squared up to 2.56 is the worst reasonable case, and it's done because it's safe. The reason Ofcom did it was it certainly does apply to Yagis, because although you get far more reflection from a vertical polarized signal than you do from a horizontal one, you do still get ground reflections, and there will be somewhere where that will be 1.6. So what they've done is they've taken the worst case and said that we can guarantee that you will be compliant if you use our formula.
Yeah, I think that's right, but it's being ultra safe and making it harder to actually become.
Yeah, agreed. But do you know the other safety factor that nobody's mentioned is occupational use? We're trying very hard to persuade. I mean, it used to be the case in America that an amateur's family could be treated as occupational users because it was assumed he could brief them. But FCC have now taken that away so that it's only the amateur who will be at occupational levels. The difference is a factor of 5, by the way, between occupational levels and general public levels. And it's another safety factor they've arbitrarily put in. But what we're working to try and persuade them to do at the moment is to treat your friendly ham who's helping you as an occupational user and not a member of the general public. So he can come in and benefit from the 5 times limits when he helps you win your shack to run your big powerful transmission. At the moment, if you've got any member of your family or any other amateur around, then you have to comply with general public limits.
The other thing that I don't think...
Sorry, George, can I just ask if Graham has got an answer to his question there? He might have left the call.
No, I'm back on sound. Just a minute.
Oh, good. Sorry, what you done there, Graham?
I've clicked the wrong thing. Right, come on, wake up. There we are. Right, no, thank you for that. No, first of all, yes, temporary installation, 5/8 on the top of a car, rig on, rig bro inside, got to use a handheld, can't get there on 2, etc. If fine, okay, and obviously you don't let people lean against the car and you park it out the way. Right. Coming back to exposure of transmitter engineers, has there ever been any sort of survey, please?
Ian White was the expert on this because he worked for, I've forgotten the initials, but the predecessor of Public Health England, I think it was, Health Protection Agency or something like that he worked for. And he says that certainly as far as amateurs are concerned, and this is backed up by other people, there have never been any cases of amateurs suffering problems from non-ionizing radiation. Sorry, I was struggling for the term. No, I was going to say
nobody has ever suffered from colour TV transmissions either, which are often at megawatt power levels.
I've heard apocryphal stories of engineers being in the middle of a very large tuning coil, and they actually knew when the antenna had been tuned up correctly because they felt their whole body get slightly warmer.
Of course.
And here you're talking about sort of half a megawatt HF broadcast transmitters. People were never concerned about those sort of things.
When I was at Vodafone, there was one of the chap in charge of all the installation of the antennas. He actually had a very severe form of leukemia, which killed 9 out of 10 people, and he was the 1 out of 10 that survived, and he got that climbing past live TV transmitters.
No,
Hannington.
I think you can't say that he got that climbing past that.
Well, I think it was.
That's no. Correlation.
That's what the doctor has said anyway.
No.
Yeah.
The doctor's bollocks in that case.
To use the phrase,
correlation does not imply causation.
Yes.
The other comment I can make in answer to that is I have worked on very, very high power radars, as David knows, for many years, and we have had people who have suffered damage from getting in the way of high power jammers.
Yeah.
In service.
There used to be a thing where particularly things like the eyes were very sensitive. So you have the 10 milliwatts per square centimetre limit, for example, because of restricted blood flow in the eyes and that sort of thing. But the effects there are primarily concerned with heating effects, affecting parts of the body where blood flow is very, very low.
Yep, that's true. There's also work going on at the moment on what are called limb currents, because believe it or not, we think from the modelling that's been done by Peter and Rick, the guy who's the expert on that from the US, that in fact the limb currents are even worse than the peak currents So we're expecting IGNIRP 20 next, whatever that is, 2025, will actually have even lower limits. And the danger is that these limits might get low enough.
So can
to
we
cause us
effectively
problems.
say that we don't know what the actual safe limits are, but Ofcom require us to comply to a certain set of limits, and therefore we have to comply to those limits, whether they are appropriate or not doesn't really matter. In terms of our license, those are the limits.
Well, we don't have to comply with the limits. We have to do an assessment that says that we will only operate the station in a way that doesn't exceed.
Okay, I believe that's semantics.
It's very important semantics, because if I do one calculation and say I'll operate
if you do not comply.
John, I'd like to raise a point.
Yeah, go ahead. Go ahead, John.
Well, thank you very much. Very interesting. I wasn't too concerned originally when the calculation came out from Ofcom. I ran some calculations. I have a very typical station, 100 watts, inverted V, up at 11 meters. Didn't seem to be too much of a problem. But now that you're talking about the ends of the antenna, which are tied off to a tree, 3 meters up from the front garden, close to the pavement, I begin to see that any kids playing outside are suddenly in this zone, and 100 watts, I'm in trouble. And I find this quite worrying.
Yes, I think that, you see, the calculator won't build that in at the moment. But what we're trying to do is we want to be responsible citizens. We want to make recommendations about things you shouldn't do that could potentially be dangerous. And the worst of those is somebody touching a bare conductor on your antenna system.
No, I don't think that's an issue. I mean, we already know about that. So obviously we've got the ends 3 meters, maybe 4 meters above the ground, but somebody's standing under that tree. His head is only 2 meters away from the end. 100 watts at 10 meters, and according to your near field calculations, he's in the zone. So, it's a bit tricky tying your antenna off to your neighbour's fence if they're sunbathing the other side. I find this quite concerning right now.
But what's changed since yesterday?
Yesterday,
when you didn't know this.
Yesterday, I did the calculation from the centre of the antenna. I didn't realise the issue of the end of the antenna.
And also yesterday, you weren't really required to comply to anything.
Well, you kind of were. It's just, I mean, the point is, what they're changing is that you've got to document that you've worked it all out properly. But it's always been a requirement to be safe, and that these standards are the implied safe limit. So it was always implied that you had to do this.
Okay, so, but yeah, okay.
Can I ask a question of John?
Yep.
Go ahead, Bill.
This is really about motivation. Obviously, there are regulations about exposure to RF fields, and there is a coming requirement to document that as amateurs we have made best efforts to know if we're compliant or not. And there's also input from Ofcom and from the RSGB. I assume the goal there is to come up with some sort of gold standard form that can be used by the bulk of amateurs and will be accepted whether you're compliant or not, and the model will be deemed to be good enough. But what I'm concerned about is, when is the document actually going to come into play? Is it going to be used as a mechanism for Ofcom to deal with complaints and perhaps shut stations down if they haven't done this document, or they've made a mistake on the form, and obviously a whole lot of other things that stem from that?
I'm caught in a cleft stick here because we're trying to do the right thing and do the good job and make it as easy for people as possible. But I think when will it be enforced? Very seldom. And on one of my early slides, they said that they basically wanted to encourage people to look at it and do the right thing and not use configurations which might be dodgy. But they weren't going to be heavy-handed on enforcement. But if somebody was obviously abusing it, like they were causing lots and lots of problems, then they would prosecute. So it's a bit like the 10 years in jail for coming into the country from the wrong place and lying about where you came from. It's a deterrent. It's not, I think, likely to be enforced. But the thing that I think a lot of people have found is how many configurations. I mean, I've just put up here a 20-meter SSB processed RG58 feeder, reasonably long, 10 meters, and you know, you're compliant everywhere. When it keeps coming up with these sorts of simple calculations. So I think it's going to be quite easy for most people to run the calculator and prove that they're compliant.
John, are you
not compliant if it was an inverted V? Because if you tie that off to the fence, you've got to have everybody 4 meters away.
I'm not going to argue with you because you're right. But if Ofcom don't actually put that constraint into here because they feel that all of the safety factors are in there, and there are tons of them. There's about a times 20 on safety factor between all the various things that go into it.
Yeah, no, I'm not going to argue. The facts are the facts, and what's happened here is you've drawn my attention to the fact that a common aerial that a lot of us run now has to be considered quite carefully in the light of this. Tying it off to the neighbour's fence at 3 meters up so it can't be touched is not good enough. You know, and you're running a modest antenna with a modest amount of power, a very, very typical rig, and you're going to have to pay attention that what you fill in this form is you know, going to be legally binding at some point.
Yeah, but if you, I mean, the one I've run, which is an inverted V, the Ofcom separation is 4 meters. So if you've got 3 meters in height, if I change, I know this is artificial, but if I change this 10 to 3, which is a bit artificial, your neighbour would have to stay 4 meters away, which might be possible.
You don't actually know. You know, he might, if you know, it's dark now. If my neighbour's, I don't know, painting the coal shed outside, how would I know?
You don't, so you have to assume that your neighbour could come right up to your boundary. I think you have to work with that assumption. You can't say, oh, the neighbour's standing on the other side of the garden, so that'll be fine. I mean, because you can't reliably do that all the time. I don't think you could demonstrate that you would, you know, you're continuously checking that. So
and what happens if he's standing on a step stool, for example?
You're
right,
really required to demonstrate that you've done this calculation.
Yeah. Well, the way you would get around that is you would run it at 100 watts, which I've just done, and then you would have in your operating procedures that you were never going to use that antenna at greater than 100 watts at night or any other time when you couldn't be confident there was nobody there.
John, you mentioned one of the problem antennas to model was ground planes. I mean, I've got an 80 vertical for 80 meters fed against you know, a whole collection of ground radials, and I do run 400 watts into that if I'm trying to work DX on 80 meters. Presumably at some point though, this spreadsheet will support that kind of antenna. Is presumably you just haven't had a chance to do the calculations for it yet.
The modeling's okay, the calculations are okay. What I was trying to say is it is a problem because the distances you have to, the spreadsheet doesn't work with 0 feet, unfortunately, because it gets square root of negative numbers. But
Oh, if you've got the radials in the ground, you mean?
well, but with what happens is that the full distance and a bit more, well, this is the case where the 1.6 really does apply, but the full distance has to be horizontal. That was what I meant by it's a difficulty, and it is difficult to comply with, but it is a common antenna, and we have modeled it. The difficulty is that depending on how many radials you put in and what the constitution of the soil is, varies enormously the answer you get. So
So the difference here is that Dave's got an antenna where the radials are in the ground, whereas my antennas all have elevated radials, but they're not that high. They're about 1.8, 1.9 meters. So how do we enter that?
You won't get sufficient. You won't get radiation. I mean, the purpose of the ground radials is to return the ground current. The ground radials themselves aren't really an effective part of the radiated system.
Well, I would dispute that completely. But I think that's a common mistake. They are.
Of whether you're treating them as an antenna or not, if there is current flowing in those ground radials, you will be much closer to that than you'll ever be to the vertical part of the antenna.
If they're elevated radials, and typically you'd only have a couple or four of them if they're elevated, then they'll take a lot of current, not the full current, but they'll take say a quarter of the current.
But
they are dangerous.
I've got 36 ground radials spread over. We're using about a
yours
kilometre
are in the
ground. They're in the ground, and there's about a kilometre of wiring just for those ground radials.
Yeah, but they'll still induce current. It'll just be spread out more.
Yeah, exactly. The effects will be very diffused.
Yeah,
it's not magic because it's a ground radial system. It's just the fact that it spreads out, so you know it has a certain effect. You just have to calculate it. But what I was going to also draw attention to is that a common problem is that people have rather more radiation coming off their feeders than they probably realise, because a lot of commonly published methods of joining things up I don't think work as well as perhaps they ought to. A lot of people, you end up, you find that they're radiating more from the feeder than from the actual what they think of as the antenna. My definition of the antenna is the part that radiates, and the aerial is the part that people think is radiating, which is completely different. And so you do have to be quite careful, and this is possibly where a punk measuring system, just to check you haven't got something stupid going on, to check that the sort of fields you're getting around things are what are as per the calculation, as opposed to being completely different, because you've got some kind of an error situation which you didn't know about.
Absolutely, George, I agree. And the measurement using a probe would be very useful for that.
Yes, indeed.
I think what is being shown to us at the moment, though, is the appropriate thing there, that their Ofcom are not requiring a higher standard. They're simply asking you to try and work out that you are compliant.
No, they're asking you to document it. That's what they're asking you to do.
Yeah. So, but
why have they?
They're not trying to. Then, if you have all of these concerns about there's this and there's this and there's this and there's this in terms of feeder loss or feeder radiation or whatever, well, you know, that's a very complex situation. I don't think they're asking you to try and go there. If you
they're not, but it's fun, isn't it?
Yeah, if you can simply say, I've modeled this and I've done this on this spreadsheet, the one the RSGB has sent us, or even the one that Ofcom produced in the first place, and it says, well, I'm compliant, or maybe I have to watch out for when people go down the end of the garden. That's enough.
What I'm proposing, Russell, is that you do the simple calculation using the Ofcom calculator, then you use a probe just to check that it's okay.
I don't think that's appropriate, Mike, because most people don't have access to
I think you're overcomplicating it, Mike. If you do a calculation and your separation distances are well within margins of safety, there's no point doing measurements at all. Just it's not necessary.
And that is that what the calculations have assumed that the system is a particular, working in a particular way, and if it isn't, your calculations are completely meaningless.
You're missing the point, George. Ofcom are not after exact science. They're after a series of methods.
Documentation.
Yeah.
So just to prove to Mike, this is my E-field probe that I use for taking measurements, generally for EMC, but we are planning to do probe measurements just to make sure our models aren't stupid. And we're going to use E&H field probes, which I've got here. And we've got one of the standard Roden-Schwartz spectrum analyzers, and with all the built-in procedures, so it will run the receiver in the right way. And the other thing I was going to say to Mike is I did tell him, but the EMC committee actually use a TEM cell much bigger than the one that Mike's built to calibrate our 1 meter loop antennas and all the other antennas we use. So it is a valid method, and David Lauder described it in a recent RADCOM. I'm just going to take one more question if I can, and then duck out, if that's all right.
Could I share a screen, Simon?
I'm aware it's getting quite late, and obviously John has been talking to us for quite a long time now. So I think you mentioned, John, you had one last thing to say. If we do that one first, and then
no, I said I'll take one last question.
Oh, right, okay, fine. So yeah, go ahead, Vin.
You choose.
Yeah, may I share a screen?
Yeah, go for it, Vin. Yeah.
I have a question.
Can you see that?
Yes.
Yeah.
You're too late. You're too late, Graham. That's question number 2.
That is about a third of my top band antenna. The bit going off to the right goes up to the feed point, and the northern bit goes down to the front garden and along the fence along the road. So you can imagine the problems I've got.
My recommendation is that you don't use red wire.
Well,
I've just done that drawing. Just to
show I think the problematic area there, Ben, is that because you've got one end tied off, which will have quite a high E field on it, by the neighbour's fence. I think that'll be the area of concern. So you'd have to have some way of trying to raise that point further off the ground, by some means. Don't know how.
Why don't you try another bit of wire that only goes as far as the highest point on the tree, and see what difference in gain you get, and you may be able to live with it.
Yes, there is about 230 feet of wire all told. The point is that the left-hand wire coming down to the fence is cross-polarized with the right-hand bit of wire coming down the other side of the garden. And my hope is that the two don't interact because they're cross-polarized.
But really, the longer wire is not going to give you much difference in transmitter efficiency. It's only going to give you better reception. So what you could do is have a very, very long, I've forgotten the word, but beverage, isn't it? Beverage antenna along the top of the fence that you use for receive, and accept a little bit of inefficiency in your transmit for making sure that your field doesn't go near your neighbours.
I mean, I only use it at night when top band's a bit better. I have no idea who's in the garden next door or what.
Well, maybe one way of solving that problem, Vin, is that you install an infrared camera, and you just make sure that when you're transmitting, that your neighbour is not in the garden near the end of that point.
Yeah, I'm being, I'm just being, provocative. I don't use it very often.
On the other hand, top band is like 32 watts, so you're hardly likely to be heating your neighbours up very much.
Well, it's only 32 watt limit above 1.845. Below that,
Indeed,
it's
but I think
below
this
that
antenna is probably more of a chat local antenna rather than a DX antenna.
Well, I can work around okay with this, but as you say, there is a 100-watt section, and I have used it.
Just as a really stupid question,
I'm going to finish.
Once this is all in place and Ofcom requires us to document this stuff, if you don't actually know what you're doing and can't work the spreadsheet, will the EMC help desk be helping out the way it can with interference at the moment? So, you know, the usual volunteer best efforts, and it takes a while.
The answer is no, the EMC help desk won't, but we probably will have an EMF help desk because it's a different skill set.
Cool.
But that is the biggest problem we have. You know, every time I talk to her, there's been, I think, 30 of us on here tonight, or maybe even 40.
We've had 40.
Yeah, there's a lot of people.
40. Everybody has their own particular configuration, and why can't you just model it for me? And the answer is that I need to sleep.
Yeah, I think also it's where the amateur clubs are going to help a lot, because, as you know, we've got various different people with different expertise, and they can sort of work together to you know, to help out with the support of the RSGB.
And my last request, as I sign off, if I may, is that if any of you can help us in any way with doing any modelling, and I guess Mike can, or any measurements, then the more the merrier. We have the expert team, but they can't do everything. They have the right tools for the modelling and stuff. But if we want to do some, I mean, inverted V simple checks at low power to make sure that the models are scaling correctly, then it strikes me as being an ideal thing for a radio club to do if they've got some equipment. So I would appeal to Reading. I think it's Reading, isn't it?
Yeah, Reading and a few blowings.
And I used to spend a lot of time in Reading because I was one of the technical directors of Rakel Electronics for many years in the defence side, and part of the time I worked at Bracknell, so I know the area quite well. I worked for Rakel, and I just wanted to say thank you very much.
Thank you, John. Thanks very much.
Yeah, thank you, and
thank you.
And thanks for all the work on the spreadsheet as well. You know, that's for trying to make it easier for people is very much appreciated. And I'm sure later, let's hope sooner or later we can get back and meet up outside. I'm sure there'll be a lot of people that would love to do some experimenting with antennas outside and measuring the field strength.
See how many RADARC members we can warm up with 400 watts.
That's it. Yeah.
Thank
you very much, John.
Now, but I can only warm myself up.
I'm sorry to go now, but I've actually been on 3 nights this week for 2.5 hours on.
Oh, you're kidding.
Yeah,
thanks very much, John.
That's appreciated. Thank you.
Yeah, thanks, John. Take care.